Hi everybody, welcome back. Example 511, we're going to be continuing our chapter on Newton's laws and forces, and this is going to be another example of the use of tension, and more specifically tension to create what's called a mechanical advantage. You may have heard in science classes when you were younger, or even currently, of simple machines like levers and ramps or I should say inclined planes. But also a pulley. A pulley is a simple machine, and what a pulley does is it doesn't do any work for you, but it makes work easier because it takes a force that this guy is going to be applying right here. The mechanic, he's applying a downward force, and first of all, it wraps it around corners, so that if he wants the engine block to go up, he has to pull down. It's going to be a lot easier to pull down, right, than pull up. But what it also has the effect of doing is doubling the amount of force it's able to apply. Because what the pulley does is it has a tension force coming off this side of the pulley and this side of the pulley as well. So we have double the advantage. Okay? So let's write a statement about, first of all, this engine block. All right, so the mass of the engine block is 100 kilograms. All right, and the acceleration of the engine block that we want it to have is 0.5, that is 1/2 meters per second squared. Okay, so with that, we should be able to write a statement about the net force on the block. The net force on the engine block, or on the engine, is mass times acceleration. All right, and already we're in good shape because we know both of those right there. But what we also need to do is we need to write a statement about the net force on the engine block in terms of the component forces. All right, now why does there have to be any kind of force applied to the block at all? Well, because the block has weight, it's massive. And so the mg, the mass of the block, which we know, times gravity, is acting downwards, and that's creating the weight force. All right, but the good news about this system, the system of pulleys and doubling your tension right here, is that, in fact, I'm going to erase that force there for a second. I'm going to call the force that he is applying to that block, I'm just going to say his hands are creating a tension force. All right, which is going all through the string, and we know that the tension force acts both ways. All right, tension, 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 all the same tension right here. But what we care most about is the engine block. And so coming off the pulley attached to the engine block, we have tension this way and tension that way as well. Both directed upwards and both created by the force of his hands. So his hands, that is the mechanic, is creating this tension and string right there. So what we can say about a statement about the net force on the block is that the net force is going to be equal to 2t. 2t. And by the way, t is that force. How hard must the mechanic pull? That is that force that he has to create that tension. That wasn't a very good 2, was it? I'm going to erase that and rewrite it again. It's going to be 2t in the positive. All right, so I'm calling the up direction, the green direction, positive. In fact, you know what? I'm just going to write t plus t. All right, both of these are acting upwards, and of course, what's acting downwards is weight, the mg force. Okay. So we have our statement, you might say our global statement about the net force on the engine block, mass times acceleration, which we know, and also the component statement, tension up plus tension up minus mg is going to be equal to this mass times acceleration. So, like I said, since these are equal statements, let's just go ahead and set them equal to each other and solve for that tension. All right, now I'm going to write 2t. All right, t plus t, 2t right here, minus mg, right, minus the weight force of the block, is going to be equal to ma, mass times the acceleration of the block, which we know. All right, let's solve for our T. Let's solve for the tension that the mechanic has to apply. Let's see, I'm just going to go with black for now, since the color is so that you know where everything came from. All right, I'm just going to stay with black. We're going to subtract over add over the mg to the other side. All right, so it's going to be mg plus mass times acceleration. And then once we do that, we're going to divide the 2 down to the bottom as well. And then we have a statement for our tension. That is, the tension that the mechanic has to apply. By the way, I just noticed something right here. Notice how this tension pulling up right here is created by the mechanic pulling down. This T, down arrow, and this up arrow are basically in the same direction, but what the pulley does is it changes the direction of the coordinate system. So if going this way is positive, or we can say that going this way is a positive direction because that pulley changes the direction. Anyway, let's just go ahead and solve for T by plugging in everything that we know. In fact, I'm going to take this numerator and make it a little bit simpler by factoring out the m, right? So T is going to equal m on the outside times g plus the acceleration, all divided by 2. All right, so that's 100 kilograms times 9.81 plus 0.5, right? So the acceleration of gravity plus the acceleration of that the lift or that the engine has, all divided by 2. And that's going to be our tension in the string, which is, you might say, how hard the mechanic has to pull in order to get it the engine to accelerate upwards. So that's 100 kilograms times the quantity 9.81 times 0.5, all divided by 2, and I get 245 newtons. 245 newtons. That's how much tension is in the string, or, well, probably not a string, more like a rope or even a chain, all right? But it's all created by our mechanic pulling down. Now again, if you were to divide that by 4, it would give you the poundage. And again, we're more familiar with pounds, and so that'd be about 60 pounds of force. So you'd have to be pulling down with the equivalent of 60 pounds of force in order to get that 100 kilogram engine block to accelerate upwards. All because of a mechanical advantage, doubling the force through ropes and pulleys. All right? Any questions, please let me know. But in the meantime, thanks for following along. I'll see you on the next one.